Hello and greetings everyone. I'm Ned Petrovic, a teaching assistant at the Faculty of Electronic Engineering, University of Niš, Serbia, Department of Computer Science. In what follows, I will present you our paper that we wrote together with my colleague Isam Alazoni from Al-Ain University, which is entitled On Persisting EMF Data Using Blockchains. It is now already here that blockchain has went much beyond finance and economical use cases. During the years, both researchers from academia and industry have tried to adopt it within many other fields and domains like healthcare, like entertainment, intellectual property, and even government. Every time we actually want to make use of blockchain's properties, which are like immutability of the blocks which are stored as outcome of transactions, irreversibility, and ability not to actually add any new transaction without consensus of the other participants within the blockchain network, it's actually every use case which requires to store data in a secure, immutable, irreversible and way which is not possible to alter and delete the data later, it's actually the right kind for blockchain. So, in synergy on the other side with another concept, which are smart contracts that represent computer programs that define how these transactions are performed relying on blockchain in which data is stored into so-called blocks, which are chained, to say, by holding the cryptographic hash of the previous block, is actually one of the mechanisms that enables many different scenarios. Among them, we also have scenarios in IoT systems, each time we require secure data management and many other applications. So recently, EMF and model-driven engineering have shown various use cases and scenarios that enable interoperability and automation of many domains. However, having the data from EMF paradigm or to have tabular data as CSV format within the blockchain, which can be leveraged by blockchain applications, is not so easy task. It requires significant effort and time. So, in our previous work, we focused on actually importing CSV tabular data using parser and producing EMF models based on that. Actually, the EMF model instances, which conform to E-core meta models. So it was presented in our previous paper, but in this paper we actually want to adopt model-driven engineering approach, which actually has go to automatically generate smart contracts that enable storing EMF data on blockchain. So our approach provides solution that tackles the following challenges. First, different blockchain platforms can use various technologies to create and deploy smart contracts. So we can use different code generators to produce different type of code for these platforms. On the other side, the smart contract technology rapidly changed, and it's becoming quite challenging for developer to maintain and to keep up to date with all these changes, and on the other side with advances in the domain. So we present a use case that involves automatic generation in our particular case study of Solidity smart contracts targeting Ethereum blockchain platform. In this context, we have a set of tools that we introduce in this paper, which are actually Python scripts combined together and other existing solutions integrated in order to automate all steps in our approach, including the generation of so-called smart contracts used for storage of CSV data on blockchain. So, what is the overall workflow of the proposed framework? First, we have E-core meta model, which is domain-specific representation of data that we want actually to store on blockchain. We have E-core to UML, which actually takes E-core meta models and produces UML meta model as outcome. Moreover, we use the existing UML to Solidity profile, which creates specific UML-based meta model, which can be further leveraged by the existing UML to Solidity code generator. We actually adopted that solution with several corrections in order to keep the code up to date with recent versions of Solidity. Once we have Solidity code, it can be deployed using a corresponding platform or using simulator, so we can actually see how it behaves in practice. When it comes to the set of provided tools, you can see on the right hand side that there is a main Python script that on one side takes EMF meta model, and actually it works the following way. We have script that actually leverages PyCore library in order to interact with the provided EMF meta model. Moreover, we have Web3 library on the other side that interacts with Ethereum blockchain. We use ArcParse library for command line interface of our tool. On left hand side, you can see how actually the tool is invoked. There are two main parameters. The first one is path to the meta model, which describes the input data like domain specific meta model. On the other side, we have a path to the EMF model containing the input data itself. On the other side, we have the script that actually takes into account the configuration of contract that is about to be deployed. So we have to provide the following information: the name of the contract, application binary interface, and bytecode. All of them can be obtained using Solidity compiler, which is actually responsible for generating the bytecode for code that is actually produced in the previous step, the smart contract itself. User enters this information in the header of the script, and then we can deploy the smart contract. And the data will be imported. So here on this slide, we can actually see the case study that is a movie's publicly available open dataset for which we evaluated our approach. We have a small domain model where we have a person which has a role in a movie which is recorded in some country for some year and has some specific title, and this is actually was deployed using Ganache environment, simulation environment for smart contracts, and AssertPy was used to test the assertions in the scripts. Moreover, we measure the execution times as average of 10 consecutive runs. For that purpose, we use desktop computer with the following configuration: quad-core CPU, 2.8 GHz and 16 GB of RAM. On this slide, you can see the corresponding smart contract that was generated as outcome of code generation and used for evaluation of this case study. Finally, the evaluation results are summarized in this table. We can see the number of transactions, which is 51 in our case. We had 38 assertions that were tested in order to see if it works correctly. The tests passed in all cases. Average execution time was 40.51 seconds. And the total gas used in gas units for Ethereum blockchain in this case was this one. Now let's sum up. In this work we introduced a model-driven approach which leverages meta models and automated code generation in order to automatize the importing of EMF data and its persistent within Ethereum blockchain, making use of Solidity smart contracts on the other side. According to our results, the proposed approach was quite successful and it enables development of all the necessary assets for blockchain-based data persistence, which reduces both the time and effort which is needed for manual operations, which can be quite daunting. In future, we plan actually to add support for other blockchain technologies like Azure blockchain and Bitcoin, and also evaluate the approach in other scenarios like IoT-related applications. Thank you for your attention.